So, this is the last session. Yesterday I finished in the middle of the session on diagnostics based upon combination of absorption and scattering. And we finished with this curve, which showed that it was possible using photon time of flight to make measurements of the absorption in the absence of scattering. One of the students pointed out there's a mistake in one of the slides. The velocity of light in tissue is equal to the velocity in vacuum divided by the refractive index, and that should be 3 times 10 to the 10 centimeters per second divided by about 1.5, which is then 2 times 10 to the 10 centimeters per second, or 2 times 10 to the 8 centimeters per second. So there's a couple of missing zeros in the slide where it says the speed of light. So thank you for spotting that. I told you it was a deliberate mistake, but it wasn't. It was just a real mistake. What about the application of this ability to measure the speed of light or the propagation of light with time? What about the application of that to imaging? And so one idea, the problem when we try to make an optical image using diffuse light is that we lose the resolution because, in fact, let me put this up for a moment to make a drawing. We lose the resolution because if I have an object here and there is no scattering, then of course I can say where this object is. But if there's scattering everywhere, then you get very poor contrast and resolution. And so one idea is to use the fact that the longer photons have scattered more, and the photons that have only a short propagation time scatter least. So if you just choose this window, so you put the pulse of light and then you only make the image from the light that arrives to the detector within the first short time interval, then these photons have not scattered very much. They are close to straight through. These long photons have gone a long way. And so this is a picture of a pattern on the surface showing sharp structure. And this is a picture just of these photons. If you put 1.5 centimeters of chicken on top of this. So you take a piece of tissue, easy to take chicken, you go to the store and you put it on top of this pattern. Of course, if you try to read a newspaper through a chicken, you're not going to be able to do so. Okay? If you take your chicken from dinner and put it on top of your newspaper, you can't read the news. Okay? But if you take the chicken and put it on top of the newspaper and you have pulses of light coming through and you only look at the pulses that come a short time after the source, then you can read the newspaper through a chicken. So it's a very useful technique.
You believe that those are almost ballistic?
Almost ballistic. So these are the photons. Oh, I keep losing the chalk here. These are the photons which I've lost the thingy. Okay. So again, we have the object, the so-called ballistic photons. So these are the photons which deviate only a little bit from straight through. These are the ones which have a big deviation.
Those photons are the ones that arrive like in less than a nanosecond, right?
Well, remember,
The whole scale was
1 nanosecond was 20 centimeters, so that's a long way off.
yeah.
Right, so you could go a long way from the axis in a nanosecond. So these,
you're talking about picoseconds.
you're talking maybe 10 picoseconds.
How can you make an image of
Because you have a pulse source and your detector has a gate that only opens, an electronic gate that only opens for 10 picoseconds, synchronized to the light pulse. And there's actually 3 or 4 different ways to do that.
Okay.
Yeah. Just an optoelectronic trick. The other possibility, of course, now you throw away all of this light. So another possibility is to use all of the light, but measure the average time that it takes the light to go through the tissue. And that's called time of flight resolved imaging. So you measure the average time of flight at each point. And in that case, you get this sort of picture. So this is a picture of a rat. So if you take a rat and you hold it up to the light, an intense light, this is what you see. Almost no internal structure. However, if you're able to time the light coming through the rat and you make a picture of the average time to go through the rat, this is the picture you get. So you start to see internal structure. It's not great, not like an X-ray, but you do start to see this is the heart, the spleen, etc. And in fact, it's cheaper to measure the average than it is to put a gate. So it's a cost issue, and you have more signal, etc. So the big.
What wavelength are those images?
This is I don't know if it even says. This was probably 700 nanometers or. This is the big interest in this for medicine, for clinical diagnostics is optical mammography. Can you do optical imaging of the breast instead of X-ray imaging? And the reasons to do this are that this is low risk, it's not ionizing radiation. Most importantly, you get functional information, not just structural information. So it tells you about the blood, you can make the oxygenation images, etc. Perhaps importantly, it can be used in young women. It's very difficult to get good mammographs in women less than about 40. Because the breast is X-ray dense, so it's difficult to get good pictures. So most times, if you're less than 40, it's very difficult to get a good mammographic picture. Whereas for light, it makes no difference. Obviously, the big challenge is because of the multiple scattering, the resolution is low and the contrast is low. So this is what happens if you just make an image through the breast. You see, you can make an image through the breast, but the resolution is very poor and the contrast is poor because most of this light is scattered, so any information is on a big scattered background. So many groups have worked on this for the last 20 years. The problem is not yet solved, but it's getting close. So I just do this slide not to go into detail, but just to indicate that, for example, there is this sort of system that is presently in clinical trials for breast mammography. So a number of groups and companies have taken this all the way through to being basically clinical prototype instruments. So the woman walks up here, lies down flat, the breast hangs down into this area, and inside there is a ring of optical fibers delivering the light to many points around the breast, and also detecting the light at many points. So you put the light in here and you measure everywhere around, put the light in here, measure everywhere. So you do a tomographic slice image and you get these sort of pictures. And you notice, for example, these images are at different wavelengths. So this is 750, this is 830 nanometers. So you can make images at different wavelengths, which of course have different hemoglobin, oxyhemoglobin absorption spectra. And then this is a reconstruction of the distribution of deoxygenated hemoglobin. And so this starts to be functional imaging. And here's another example in color coding. And it's been possible, for example, to extract from this information at different points in the breast measurements of the metabolic rate and measurements of the blood perfusion. And you start to see that these are normal patients, or these are patients with breast cancer. So this will never be an imaging technique that will have very high resolution. Probably the best resolution that is possible in theory is maybe 5 millimeters. So it's not a high resolution technique. It's much more like nuclear medicine imaging, like radionuclide imaging, where you have fairly low resolution, but the possibility of functional information. And then you can think, of course, about adding optical contrast. You could give an injection of an absorbing dye. You could give an injection of a fluorescent dye and measure the fluorescent emitted light and so on. So there's lots of interest in this as basically a non-invasive method of doing functional breast imaging. So you would...
Fluorescence will not make worse, I mean...
No, it makes it better.
With the ballistic photons.
Well, this is really diffuse photons. Yeah.
So those are diffuse.
These are really, you really with the ballistic photons, if you do the gating, it really is impossible to do that through more than about 2 centimeters. If I showed you the 1.5 centimeters of breast, if you go to 5 centimeters, to put the gate on, there's simply not enough light to make the measurement. So this is functional imaging with diffuse light. So it's pretty interesting to see in the next 5 years whether this becomes part of the routine clinical diagnostics, or maybe it'll disappear again. But when you get to this sort of clinical technology, it starts to look pretty feasible. So, still on absorption and elastic scattering, of course, I just showed you this is diffuse light. You can also do elastic back scattering. So now we're going to be doing measurements with the light coming into the tissue, and we're going to be looking at light that comes back, with virtually straight back, elastically scattering from some structure, like specular reflection, like Van der Lee's bald head again, okay, but deep within the tissue. Okay. So it's a very good demonstration.
Like having the laboratory with you all.
Absolutely, it's great. So there are 2 classes of technique. One is called light scattering spectroscopy, and the other is called optical coherence tomography. This is probably more familiar, and this is less familiar. I'll start with this. So the idea in light scattering spectroscopy, and this is mainly for hollow organs, so bladder, esophagus, etc., is if you take a pathology slide and you look at the lining of the esophagus, you find that this is normal tissue and this is precancerous. And obviously there are structural changes. One of the big change is that in cells that are starting to become cancerous, the nuclei are larger. And that's to do with the replication of the DNA, the so-called ploidy increases. So these nuclei are larger. And in fact, when the pathologist looks at a slide, that's one of the main things that they're looking for. Does the tissue have large nuclei as an indicator of pre-malignancy or malignancy? So the question was asked by a group at MIT about 10 years ago, could you make an optical system that would be sensitive to the different nuclear size without taking the biopsy? And so they introduced this technique called light scattering spectroscopy. And the idea is, if I look at a piece of tissue, let's say this is a piece of esophagus. Why am I, even if you had the resolution, what prevents me from seeing the cells on the surface? And one of the big things is the fact that there's so much light coming from all the multiple scattering from below the surface. So if you could get rid of that multiple scattered, the diffuse light, maybe you could just focus in on the top layer with higher sensitivity. So the idea, there's a couple of ways to do that. One of the ways to do it is to put polarized light into the tissue. The light that scatters many times has no polarization left. The light that backscatters from the very surface is still polarized. So if you then cross-polarize, you can eliminate a lot of the background signal. So that was done. Basically, you take the light source, you do this at different wavelengths, you shine the light onto the tissue, the light comes back from the surface layer and from the deeper layer, but then you cross-polarize so that you eliminate this deeper tissue. And so the idea is to get rid of this stuff and just leave the signal coming from the top layer.
But the light that comes from the deep part is not polarized.
Right. So these two things are parallel polarized.
Oh, parallel.
Parallel polarized. Sorry, did I say cross? So parallel polarized. So that the light from here or from here has the same polarization, whereas this light has no polarization. And if you do that, you get spectra. So this is the signal versus the wavelength, which has all this fine structure in it. So normally you see a spectrum which is just a smooth spectrum. So here's all this fine structure, and you can fit this fine structure mathematically to a model of particle scattering. So we say this layer is made of particles. So let's assume that it's made of spherical particles. We fit these curves to the Mie theory, which is a physical description of scattering from particles, and we can calculate the size of the particles. And if you do that, you find that in regions of normal esophagus, you have a certain size of particles, and in regions of abnormal esophagus, the average particle size is larger, because you are picking up the larger nuclei in the cells. And then you can color code that. You can say we'll make red correspond to the large particle sizes and blue correspond to the small particle sizes, and you make a map, and you can start to get images, which is really images of the average nuclear size at each point on the tissue. And since the average nuclear size is a marker for cancer or pre-cancer, so you can basically do pathology without taking the tissue sample. So that technique is quite nice. The second technique that is a lot more common is optical coherence tomography. This is the optical equivalent of high-frequency ultrasound. Now, when you do ultrasound imaging in tissue, you send a pulse of ultrasound. It goes into the tissue. Some is reflected. Some of that ultrasound is reflected, and what you do is you measure the time delay between the sound going in and the echo coming back. So it's like the same way as bats find their way around. What's Portuguese for bat?
Morcego.
Okay, so morcego. So they send out a pulse of sound, they listen, they time the length of time for the pulse to come back, and then they know the distance to the object. Now, in principle, you can do that with light. You send a pulse of light, and you measure the time for that light to come back. But in practice, that's extremely difficult. We saw that in the diffuse, you need time limits of picoseconds. So 1 picosecond is 1/5 of a millimeter. Here we want to make images with a resolution of 10 microns. So you would need to have a time resolution of a fraction of a picosecond. So it's just not possible in practice. So instead of that, they use a technique which is known in physics for 100 years, which is to use interferometry. So now we take a light source, we split it. This is just a piece of glass. Half of the light goes to the tissue, half of the light goes to a mirror. Light comes back, interferes, goes to a detector. Now, if I take this laser, I've lost the bump. If I take this laser and do this, as I move this reference mirror, you get this pattern of interference. This has no information on the depth from which the light has been scattered, because the laser has a very long coherence length. That's why you can take a laser and shine it to the moon, and it's only this size when it gets there. Okay? So you have to take a so-called low coherence source, in other words, a bad laser, a laser which is coherent only over a certain distance, and then when the light comes back, the interference will localize the depth in the tissue. And so now as you move this reference mirror, you're basically scanning the sensitive point backwards and forwards in depth. And then you scan the whole beam to make a 2D image. So this is like a 2D image sliced into the tissue. This technique was, so this just illustrates this. This is 3 cover slips from microscope, so little thin pieces of glass. Here's the interference signal, and here's an image. You can even see, if you take microscope cover slips and squeeze them together, you can see the air in between the cover slips. Okay, so very high resolution technique. The wavelength, the resolution in this direction depends on how wide this interference pattern is. So if you want very high resolution, you need a very small interference length. And that's just, if you're interested in physics, that's just shown here. This is a very unusual technique optically, because in most techniques, if you take a picture with a camera, the resolution in depth is related to the resolution sideways. So if you know, if you're a photographer, if you stop down the F number in a camera, you get larger depth of view and a larger depth of focus, but less, which way around is this? Smaller depth of focus, but more sharp. In OCT, the axial resolution is completely independent of the lateral resolution. The axial resolution depends only on the length of that coherence pattern, the lateral resolution depends on how tightly you focus. So it's unusual from an optical engineering point of view. What does all that mean? This was first developed for ophthalmology. So this is a picture looking in the back of the eye with a normal so-called fundus camera. And if you were a very skilled ophthalmologist, you might be able to see that there's a region here that looks a little unusual. If we take the OCT and we make a section through there, this is a section you see, so this is underlying, so here's the top of the retina, and you see this patient has a hole in the retina, probably caused by being hit on the head playing soccer, which is the commonest sports injury or the commonest causes of so-called macular holes. Okay, you go boom, and there's a sudden shock, and your eye cannot respond fast enough, and the retina tears.
Does that in baseball?
It tends to happen when you get hit on the head with a ball, right? Or when you're heading, or you go boom, so, or your wife hits you, or whatever. So you get then you have to say you were playing football. So you get these sorts, and it's very important to see these, but also so that the ophthalmologist can monitor that this is healing. Because if this does not heal, the risk is that the whole retina will lift off. This picture is what the original imaging looked like. This is similar to this. This is what it looks like nowadays. I mean, you can resolve all these different layers in the retina. Okay, just in 2 seconds, non-invasively. So it's a very elegant tool for ophthalmology. It can be used, however, not just for ophthalmology. This is a dental application. This is an old slide, so this is just a prototype. But this shows you the OCT image of a tooth where there's been an image of the tooth, and you can see the dent and enamel boundary. And you can test, for example, whether or not if there's a cavity and it's been restored. You can see whether the restoration is successful, etc. So this is quite nice in dentistry. As far as I know, it's not yet used commonly because one of the challenges in OCT is that you can only penetrate about 2 millimeters.
I think they have some time problem.
Is there?
Time that takes for
it is too long to make a scan?
There is a company in the United States that makes a fiber tip that vibrates. And it's scanned. I don't know if you know.
Okay, so that's much faster.
A probe that's this big,
Yeah.
a fiber, and a box which is interferon. Then you do a OCT in seconds.
And do you know if people are using that in dentistry?
I saw a demonstration in Japan.
Okay.
2 months ago.
Okay. So that's nice. So I mean, the information is there. It's just a matter of making it practical. If you if the light is polarized, there's an interesting application shown here. This is an ordinary OCT image using non-polarized light, and this is an OCT image using polarized light. And in this case, in fact, the skin has been burned. So you can actually see the depth of the burn here, and that's very valuable for people, for surgeons or physicians who are managing burn patients, because to be able to see the depth of the burn gives a lot of information. For the biophysics people here, the reason you can see it here and not here is that the burn destroys the birefringence of the tissue, and you can measure the
It's from biopsy?
No, in vivo.
How can I see it?
Because that's the basic principle of because when you do the OCT image, it's like ultrasound. You're making a cut through there as if you then opened and were looking. Okay. In the last 5 years or so, it's also been possible to make fiber optic based OCT systems, you replace that beam splitter piece of glass with a piece of telecom equipment called a 50-50 coupler, but it's the same thing. The light comes down, is split to the tissue, split to a scanning mirror, the signals come back, recombined to the detector. And this is an example, actually from our own lab, of an OCT fiber probe inside the esophagus. And this just shows, this technology is completely dependent on telecom. Almost all of the components you see here are straight from the optical telecommunications industry. So if it wasn't for telecom, this technology would not exist. So here's this system in our clinical prototype showing the probe in place. Here's a probe. And so the light comes out sideways. This is held against the tissue. And then this tip is scanned backwards and forwards like this in order to make a section through the tissue. And you get these sort of pictures. So here's the biopsy, and here's the OCT image, and you can see this microstructure. This is non-invasive. This obviously requires taking the picture. And here's another example. So it shows very nicely the layer structure. So if you have, for instance, a disease, you see the destruction of these layered areas. This is another example. This is in a rat esophagus. You see all the layers of the esophagus. And you can also do Doppler OCT the same way as you do Doppler ultrasound. You can make images of the blood flow, and this shows the blood flow. This shows individual microvessels, probably about 50 microns in diameter. And the color coding here tells you the velocity of the blood. Again, I don't want to go into the details. This is theoretically quite complicated to do. It's not as easy as doing Doppler ultrasound. You know, in Doppler ultrasound, you basically measure the change in the pitch of the sound. So, you know, when a train has a whistle blowing and it comes towards you, it sounds higher, and when it goes away, it sounds lower. It's not possible to do that with light because the change in the wavelength is tiny. So you have to use another technique that involves measuring phase. But the bottom line is you can get images of blood vessel showing the blood velocity. And this is examples from our clinic showing this. These are blood vessels, probably arterioles and venules in the normal esophagus. This is a patient with varices. You know, you get varices veins on your legs. This is varices veins in your esophagus, which is a problem because these bleed, and so management is difficult. And this is the shows the microvascular pattern in Barrett's. So this is the microvascular pattern in inflammation, in chronic inflammation. Okay, and you see there's a lot of more blood vessels, they're disorganized, and so on. Again, this is taken in at about 8 frames per second during endoscopy. So you get almost real-time images of this blood flow. Okay, so that was absorption and elastic. I want to talk a little about fluorescence, although I know that people are fairly familiar with this, so I'll go through this fairly quickly. So in fluorescence diagnostics, you know, everyone knows about fluorescence. Certain molecules, if you illuminate with short wavelength light, like UV or blue, will give off longer wavelength light. So in this is just a set of test tubes with increasing concentrations of a fluorescent dye, which is red fluorescence, and you can see that the more concentration there is, the more fluorescence. So the fluorescent molecule can be the natural molecules of the tissue, so-called endogenous or autofluorescence. So just like collagen is very green fluorescence, NADH, etc. So many molecules naturally occurring tissue fluoresce. And then you can use fluorescent dyes. You can give a fluorescent dye to the patient, and there's various forms of those. And you can make the images continuously, like here. You can make lifetime images. You can make resonant energy transfer, fluorescence recovery after bleaching. There's a lot of specific fluorescence-based techniques which give you different information. Here's an example of an administered photosensitizer. This is photofrin in a model with a tumor in the mouth of a hamster. And if I put the light out for a moment to orient you, so this is the hamster's teeth, the incisor. So the cheek is turned inside out. This is the cheek, and you can see these tumors. Okay, here's a tumor here, a tumor here. You don't need fluorescence to see that. Okay. And so in fluorescence, you see this big tumor here, this big tumor here. So that doesn't matter. What matters is this and this and this, which you do not see easily, if at all, on the normal, but you can see very clearly in the fluorescence. And here's an example of ALA we talked about the other day. Here's the tumor. You don't need fluorescence to see that. You apply fluorescence, you still see the tumor. But what's that? Okay, so if the surgeon was to do this surgery, he might cut around here and leave this behind. Okay, a little spot of tumor that you don't see just by eye. Here's the use of ALA in Barrett's. So you can give the patient the ALA and see the fluorescence. And here's some microscope images of the fluorescence in the tissue. As I said yesterday in the seminar, there's a lot of interest in using target-specific fluorescent molecules such as antibodies or these other molecules linked to either a fluorescent dye or to a nanoparticle. And I showed you this yesterday, the use of a fluorescent dye with targeted with an antibody to the tumor. So those are examples of exogenous or administered dyes. What about the autofluorescence? So this is the system produced by Zilix in Vancouver, and is an autofluorescence endoscope system. And basically one of these boxes is a light source, and the other box is a set of cameras. And this is the sort of picture you get. So this is looking down inside the lungs of a patient. So this is the right and left bronchial tree. And in white light, this patient would be considered normal. So this patient would, no problem, go home. If you look in fluorescence, and it's always difficult with these projectors because you lose color, but it's quite clear that this region here has abnormal red fluorescence compared with the normal green background. And when this is biopsied, it turns out to be carcinoma in situ, which is a very early stage of cancer, which is completely curable at this stage. But if the patient was sent home and comes back 6 months later, this tumor may have invaded into the submucosa and become much more difficult. This just shows the technology. This system can switch between white light and blue light excitation, and it measures actually it measures the green fluorescence and the red reflectance, but you can also do this green fluorescence and red fluorescence. And you basically make a computer image which is false colored. So if we come back to this image, the obvious question is, why do you see this difference? So a lot of work has gone in the last few years to try to understand the fundamental changes in the tissue that cause this difference. And this is complicated. You don't have this slide, I just threw it in, because many things are happening here. You can have biochemical changes, you can have changes in the structure of the tissue, you may have changes in the amount of blood in the tissue, and so on. And of course, these are layered structures where you have a certain pattern of layer which gets disrupted increasingly with disease. So, as a model for this, you can say that the detected spectrum will depend on, so here's a model of the tissue, the mucosa, the submucosa, and the underlying muscle. So the signal you get here will depend on how deeply the light penetrates to excite. It would depend on what's the spectrum of the intrinsic fluorescence of each layer, and it may be different for each layer. And then, of course, this light has to emit from the tissue, and it will be multiply scattered, as will this, but importantly, this will be multiply scattered, and there'll be some absorption. So there's a lot of things can happen here, and the question is, what is changing with disease? Is it the thickness of these layers? Is it the intrinsic fluorescence? Is it the change in the blood? Maybe you have blood here in the disease and no blood without the disease, so this will absorb the light more at different wavelengths. Just to give you an example, in this particular case of lung, it is believed that the primary change is that at these early stages of disease, you simply have thickening of this top layer. The mucosa thickens. This image is created from the ratio of the red to the green fluorescence. So this is a red-green ratio image. Here's green fluorescence, and here's red fluorescence coming out. And because the green light is absorbed more in tissue than the red light, this extra layer takes out, absorbs more of the green than the red relative to the normal thickness. And so you change the balance of the red to green emission. It's still the same fluorescence coming from the tissue, but you have a difference in the absorption of the two colors, and therefore you change the balance of the red to green, and therefore you can see that in the image. So in this case, in the lung, it is believed that simply this thickening of the mucosa, which of course is very difficult to see here, is the reason.
Professor?
Yeah?
You don't need guarantee that the fluorescence in red and in green be to the same molecule or the same.
Well, let me show you the next one, which is a colon, and you'll see that there's a difference. Okay, so that's this explanation we think is true for early stages in the lung. But now let's ask, is that the same everywhere? So if we look in the colon, remember that I showed you the video yesterday of the polyps, and you make a spectrum in the normal colon and in a benign polyp, a hyperplastic polyp. You see the spectrum, if anything, there's more fluorescence. Here is an adenomatous or dysplastic polyp. This is a pre-malignant polyp, and you see the green fluorescence is way down, and there's more red to green here than there is here. So this has tipped towards here and also gone way down. This imaging system is measuring here and taking the ratio. So now we would expect the hyperplastic polyp, in fact, if anything, to be brighter, and the adenomatous polyp to have a shift towards the red. And indeed, that's what's happened. So these are two polyps. These look identical in white light. So the endoscopist would not be able to tell whether this was benign and this was pre-malignant or the other way. If you look at the fluorescence, this polyp is even more green than the background. Okay, it's the same color, but it's a brighter signal. This one, which you see face on, actually is red compared with the background. Is it the same reason as in the lung? And to answer that, you have to look at the microscopy of the tissue. This is work done by one of our graduate students. If you make a confocal microscope image of normal colon, and this is color coded so that we have the same red to green appearance on the picture, on the images here, as happens in the actual endoscope. So you see the normal colon, you see a crypt here, and all this green or yellowy green is collagen, which is very bright green fluorescence. Now if you look at a benign or a hyperplastic polyp, what you see is that there's more collagen between the crypts. So these polyps are just a growth of collagen. There's no changes in the actual cells of the colon. They just have the same cells, but there's just more collagen growing laid down. And of course that collagen piles up and it makes the polyp. If we go to the adenomatous polyp, you see there's many more cells here. And in fact, this growth of the cells squeezes out the extra collagen. So the green signal goes down. Not only that, you find that you start to get specific red fluorescent granules in the crypts. So that unlike here, where there's no red fluorescence, in the adenomatous crypts you start to see specific red fluorescence. So we squeeze out the collagen. One of these bottles of water. You start to squeeze out the green fluorescence from the collagen, and you start to have red fluorescent particles. And you can look at the spectrum of these little red particles, and it's possible then to identify what these are. And in fact, this is the garbage tip of the colon. This is so-called lipofuscin, which is a lipid degradation product. So what's happening here is that when you start to get pre-malignant, the cells are dividing so fast that the crypts cannot clear the garbage. The garbage men are not coming often enough. And so you accumulate this basically garbage in the cells that happens to have red fluorescence. So the result of that is that this starts to appear red because you've lost the green and you have more of these red granules. So it's a completely, to answer your question, it's a completely different mechanism from what clinically looks to the same situation in the lung. So the conclusion is that for each situation, you really have to do this sort of analysis to understand it, because it's going to be different for every situation. So in the colon, what we think is happening is there's a little thickening, but actually we're getting a lot more fluorescence in the red in the adenomatous, and a lot more fluorescence in the green in the hyperplastic. So we see the bright green here for the hyperplastic, and we start to see the red in the dysplastic. It takes a lot of effort to sort this out. It's not obvious what the explanation is. Okay, so it's a mixture of structural and biochemical changes. I want now, lastly, to talk about so-called optical biopsy. So this is just a cartoon showing the notion here. So you know from the video I showed yesterday that you take biopsies. If you were able to make an optical signal and it was normal, you wouldn't take a biopsy. If you did an optical signal and it was abnormal, you would take a biopsy. So that's the principle. Let me just show that again so that to make that clear. So normally you go down with an endoscope and you take biopsy, 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 biopsy. So the idea is, can you make a test which says normal, represented by green here, you do not take a biopsy, abnormal, take a biopsy. Just to direct the biopsy, to guide the biopsy. Now, of course, you can do that with fluorescence, and many groups are doing that. But what I want to talk about is to do it with Raman spectroscopy, just to change the subject a little. So in Raman spectroscopy, well, let me put, in fluorescence spectroscopy, you have a molecule, it absorbs a photon of light and goes to an excited state. And then it de-excites, an excited electronic state, de-excites by giving off fluorescence. In Raman, the photon comes in, it does not change the electronic state of the molecule. It simply interacts with the structure of the molecule and changes the vibrational or rotational state. So the molecule has the same energy levels, but it may be slightly distorted, if you like. And that can either give energy or take energy. So in fact, in this case, for instance, if the molecule, these are virtual states, the molecule starts here and ends up here, in fact, you've given the molecule energy. Or you can start here and end up here, in which case you'll give the photon energy. So these are subtle changes, but they are very specific to the particular molecular structure. So here is a Raman spectrum. Notice it's not in wavelengths, it's now in differences in frequency. That's just because this was originally developed by chemists, not physicists. So they prefer, for other reasons, to just do wave numbers. But what you have is a spectrum which is very rich. So compared with the fluorescence spectrum, which is broad, fairly unstructured, there's a lot of information here. Each of these peaks corresponds to some particular vibrational characteristic of different molecules. So this peak here is the carbon atom and the hydrogen atom doing this. Okay, this peak here is due to the ring expanding and decreasing.
Can I do a mass spectrometry on the specs?
No. That's a good question.
To be sure.
Right, because let me just show you. These are Raman spectra of tissue. Okay, so here's muscle, here's a fat sample, here's liver. This is malignant ovarian, this is ovarian cancer, this is normal ovarian tissue. The important point is this peak or that peak of that peak does not correspond to a specific molecule. This does not tell you that this is a specific molecule. This peak is due to some particular bond vibration, and that bond may be found in many molecules. So there's a difference in mass spec or HPLC, you're looking for particular molecules. Here we're looking at the common bonds of many molecules. Okay, so it's not quite the same information. But you can see that these spectra are very, very different. Very rich information. So Raman spectroscopy has been used in chemistry labs and in biology labs for decades. But it's only in the last 10 years that it's become possible to do this in the clinic. I mean, normally a Raman spectrometer is a big box like this, and you put the sample in. So this was done in the clinic. Again, this is from our own lab, but some other groups have done this too. So you take a diode laser, you put the light into an optical fiber, it delivers the light to the tissue. So here you see it being delivered to the tissue inside an endoscope. So this fiber goes into the endoscope. The interactions take place, and the light comes back up into a spectrograph, a high sensitivity CCD, and you get the spectrum. In principle, that's very easy. In practice, there's a major problem, and that is that, as I said yesterday or the day before, the Raman signal is incredibly weak. There's 1 million photons backscattered for every Raman, and there's even 1,000 fluorescent photons for every Raman photon. So you're measuring an extremely small signal. And the problem when you do this with optical fibers is that the light going into this optical fiber generates Raman from the fiber and fluorescence in the fiber. And most of the light that you detect that comes back up here, 99.999% of it is elastically scattered at the same wavelength, and that generates more Raman and fluorescence from the fiber. So in fact, if you do this, you find that the signal is terrible. You basically are making a measurement of the fiber, not a measurement of the tissue. And so it's an absolutely critical part of this is that you're able to build optical fibers into the tip of the probe. And remember, this is 2 millimeters. So you have to have these fibers, which are maybe 0.5 millimeter in diameter at most. These filters have to be built in to this tip. And that's very difficult. But if you do that, you can then separate the information you want is actually in these tiny little peaks here. Okay. So you need to be able to get rid of this background that's partly coming from the fibers and partly from the tissue itself. In that case, you can start to produce these spectra. So here are some Raman spectra for in the esophagus taken with that system, and there's 3 different colors here. The green color is the Barrett's esophagus, the inflamed tissue. The blue is low-grade dysplasia, the very earliest stages of cancer, and the red is the high-grade, the next stage. So what are you going to do with such spectra? Right? I mean, this is pretty messy. And so the simplest thing you can do is to say, well, ooh, look at that, maybe there's something different here. Okay, so I'll measure this peak, or maybe I'll measure this peak. And it turns out, at least in our experience, that you can do that. This is some particular ratio of 2 peaks. And you plot out for each patient. You know, you say, okay, in this patient, this is the value in the Barrett, this is the value in the low grade. And you find there are differences, but the scatter is huge. And you do not have a reliable diagnostic between these. The reason for this is probably, going back to your question, this is not a specific molecule. This is not a specific molecule. So the molecular changes that take place due to the disease are spread all over the tissue, all over the spectrum. So what you have to do is analyze the whole spectrum, not analyze individual peaks. And that's done by techniques that are known as chemometric techniques, which I don't have time to go into, but basically these are mathematical techniques that allow you to take the whole spectrum and use all the information. And if you do that, you can then start to separate these tissues. So here is the normal or non-malignant Barrett's. Here is a low-grade dysplasia. Here is the high-grade dysplasia. So this is exactly what we were talking about this afternoon. So you get this nice separation between them, and if you do that, then you can calculate you can compare what you get on the Raman spectroscopy with what the pathologist says, and you can calculate the sensitivity and the specificity and the accuracy.
you're using the histological as the reference.
Ah, that's a great question.
That's 100% sure.
That is the biggest problem, right? We actually think, we have some evidence that the Raman spectroscopy is more accurate than pathology. And the question is, how do you prove that you're more accurate than the gold standard? It's very difficult, right? Because what you really have to...
If you have a third technique.
Yeah, but they're, they're all equally bad. Well, actually, let me come back to that, but to the third technique idea. But really what you have to do is a so-called longitudinal study, in which you do the measurements with the Raman, you do the biopsy measurements, and then you follow these patients and you see which ones ultimately develop cancer, etc. Right? It's a big problem. In fact, this is thank you for raising the question. A major problem in optical diagnostics now is becoming the fact that the gold standard is not good enough. So we really want to be up here at 100% certainty, and we can't get past the level of the gold standard. It's a big problem, not just for Raman, any optical biopsy, any fluorescence, same problem. So it's one to discuss. I just want to maybe finish with showing one other thing, which is also related to the endoscopy. So everyone knows about confocal imaging, microscopy technique, very common, very powerful. And basically it's a technique where you have a laser scanning microscope. Normally in a microscope you illuminate the whole sample and you look at the light. In a confocal microscope you have a laser beam that scans the sample, and the optics is set up so that you have a pinhole in front of the detector so that light from above and below the focal plane cannot enter the detector. So you can produce optical sectioning. So this is optical sections of a fly with confocal, where the fly is intact. This is a whole fly, and you just optically slice by moving this plane up and down through the fly. And here's one level, here's the next level. This is what happens if you make an image, transillumination image of the whole fly. And here's what happens if you computer sum the individual slices. You can see the much better resolution here. You can see the wing structure, etc. And this is an example, more biological example of vasculature, showing the much, much better resolution you get with the confocal than with the non-confocal. Big question, could you do this in a patient, in an endoscope? So could you take this machine and have someone swallow it? That's a challenge. That's a technical challenge. You have to swallow this microscope. Or you make the microscope smaller, which is what's actually done. So,
This, as you said, with the nanotechnology.
yeah.
Maybe you're going to have nano cameras and nano lenses.
Let me show you. Okay, so this has been done. The Australians, a company called Optiscan, which was a spin-off from one of the universities in Sydney, actually took this optics, which normally is this big, and they miniaturized it so that it could be on the tip of an endoscope. So they simply reduced the whole thing by a factor of 100. So what you have here is absolutely conventional confocal microscope that's only 2 millimeters in diameter. So you make a tiny, tiny, tiny little microscope, and you put it on the end of the end of the endoscope, and you do the images by scanning a laser beam in here.
How long does it take to have this image?
This image, well, actually, I'll show you a video. Okay, not long. not long, because you're scanning over a very, very small area. Right? So this is an example in the colon. This is an in vivo image in a patient of the surface of the colon, and you see the crypts. Remember I showed you that fluorescence picture of the crypt structure with the green collagen? So this is an in vivo image of the colon crypts. And here's another example. This is normal colon, this is colitis. You can see the changes with colitis. Here's the vasculature in the colon and colitis. So it is possible to do essentially pathology at the end of an endoscope without taking tissue, non-invasively. So this is what is the right word? This is simply saying, let's take the same technological idea and make a very small version of it. Okay. But there are a couple of ways in which you can say, no, let's take a different technology solution and achieve the same thing. So this is a group in Germany who did a confocal endoscope using MEMS, microelectronic mirror system technology. So rather than mechanically scanning by conventional but very small optics, they make MEMS devices. And again, this works very nicely. This is a, if the video runs, let's see if this will run. Oh, sorry. Oh, maybe I didn't load the video. It's coming. There it is. Okay. So this is a confocal endoscope. Those are individual cells inside the patient, in the colon. Taken non-invasively, which I think is amazing. So it's great fun. Question is, what are you going to do with something like that? Right? So the field of view of these images, is about 1 millimeter. So you're going to do that over the whole colon, which is meters squared. So what's the clinical role for that? And that's not clear. And so I wanted just to end with saying that, so we've seen a number of techniques. There's OCT, there's the Doppler OCT, you can use antibodies with fluorescence, you can use Raman, etc., etc. There is evidence that if you take more than one of these techniques together, you do better than any one technique alone. So this is an example from a study that was published a couple of years ago, where they looked at combination, singly at fluorescence, reflectance, and light scattering in this case, and then looked at the combination of these and found that if you use the combination, you got better than using any single technique. So now the challenge is, it was difficult enough to build a fluorescence camera. How are you going to build a fluorescence plus light scattering camera, or a fluorescence plus confocal camera, etc.? And so, although it's true that the combination of methods is better than any one alone, how good does it have to be clinically useful? So there's a big argument here on this topic, and I'll summarize it with this cartoon. So this is a patient going to have a colonoscope, and this is the new colonoscope. And the surgeon, this is a very enthusiastic biophotonics endoscopist, and he's saying, I agree, but in all other respects, this endoscope outperforms the rest. All right, so there's just one little problem here, is that you've combined too much technology into the one device, and you've made it not very clinically feasible. Okay. So, are these real tools, or are they just toys? Okay, and money is a big issue here to make these feasible. So I had another bunch of slides that I was going to do if I had time, which I don't, so I'm just going to ignore those. I want to come to end with this. Okay, so end where you start. So the question was, in this picture taken by my wife in Scotland, why is this clearer than this? So, one suggestion. I'll give you my theory, but it may or may not be correct. So, this is misty, right? It's always misty in Scotland. It looks like this all the time. So, you have to analyze the optics of this situation. So the optics of this situation is that you have a mountain and a lake. And you look directly at the mountain, or you look at the reflection of the mountain in the lake. Now, if there was no mist, this picture should be the same as this picture. Now, what happens if, as often occurs in Scotland, the mist comes down? Now, my theory of this picture is that the mist is only down to this level. Okay.
So it's a path of light.
All right. So if the mist is only down to this level, this light has to come through the mist. The light that you're looking, if you look directly at the mountain, has to go through a greater thickness of mist than the light if you look at the lake. Because the light coming from the top of the mountain to the lake only goes through this thickness of mist. Here, there's no scattering. Whereas this light has to go this whole distance. How many marks out of 10 for the answer? You think that's right? Feasible, feasible. I'm not sure if it's right. I don't know. I mean, there's also a question as to whether you will have polarization effects here.
What about the background? I mean, you see, by looking to the mountain, you are getting a lot of background light too.
Yeah.
And then when you look at the...
That's true. So there's, so you have all this diffuse backscatter. Yeah. Yeah. So.
They saturate our eyes or the camera. Or
Well, there's a possibility that the image also has some polarization.
That's right. So I mean, this is a specular surface, and so there's.
This is the scatter light.
Yeah.
So anyway, so that's my best theory for this at the moment. But again, this is not a controlled experiment, so I'm not sure that it's the real answer.
Look, if you want to stand to the transparencies of this one, then it's still...
Well, let me just finish this and then we'll see what people want to do. So, I just wanted to thank you for attending this course. And I hope that using this image of the mountain, that you started here and that the course is taking you up a little. So let me say thank you at this stage, and then we'll discuss whether or not to look at the other slides. Thank you.